Welcome to the Peacademia course on the basics of semiconductors. This lecture will cover the energy level in the atom structure. Let's start. By the time you finish this lesson, you'll learn the energy level, sublevel, and orbital concepts, quantum numbers, capacity of each energy level or empty states in each energy level, and the Pauli's exclusion principle. In the previous lecture, I introduced the atom structure and slightly touched on the energy level concept. In this lecture, you'll learn more about the energy level. This is a particular atom with 4 energy levels. Depending on the atomic number, this atom could have less or more energy levels. The innermost energy level has the smallest thickness, and by moving away from the nucleus, the thickness of the energy level is increasing. This change in the thickness in general demonstrates that the energy level capacity of holding electrons increases by moving away from the nucleus. As a result, in this particular case, the fourth energy level has the largest capacity among the energy levels 1, 2, and 3. Please do not take this figure as the actual geometrical shape of an atom. This is just a model helping me to teach you the energy level concept. Between each energy level, there is a gap. It is best to say a forbidden gap. No electron exists in the forbidden gap, and no electron can go to other energy levels through the forbidden gap. This is why we say the energy levels are quantized. So what will happen if an electron, let's say in the second energy level, is energized enough to be in the third energy level? What type of transition will take place? This process is not well understood, but what experiments have shown at the same time the electron disappears in the second energy level, it appears in the third energy level. The electron could be energized by photons or an electric field. To continue the discussion, I need to introduce the 4 quantum numbers. The use of the quantum numbers is a way to distinguish electrons in an atom, or in other words, their position in an atom. The first quantum number is called the principal quantum number. It is shown by the letter N. The principal quantum number refers to the energy level number. N can be any natural number starting from 1. It could be 1, 2, 3, 4, etc. The innermost energy level has a principal quantum number of 1, the second one 2, the third one 3, and the fourth one 4. The second quantum number is the angular momentum quantum number. This number is shown by the letter L. L can be any whole number. This number it starts from 0 and ends at n-1. We already know that n is the principal quantum number. If n points us to the energy level number, what L points us to? It's a really good question. To answer this question, I need to show you what is behind each energy level. Each energy level has a specific number of sublevels. The number of sublevels in each energy level equals the principal quantum number of that energy level. This might be too wordy, so let me give you an example. The third energy level has a principal quantum number of 3, right? So at the third energy level, we have 3 sublevels. The first energy level has only 1 sublevel. Similar to the energy levels, we assign numbers to the sublevels, and those numbers are nothing but the angular momentum quantum number, or L. L for the first sublevel is 0, for the second is 1, and this trend continues. For example, in the fourth energy level, the angular momentum quantum numbers are assigned to the sublevels like this. You can see now how these sublevels in other energy levels are numbered. In addition to the angular momentum quantum numbers, we often refer to the sublevels by the letters S, P, D, and F. S always represents the first sublevel, P the second sublevel, D the third sublevel, and F the fourth sublevel. To distinguish these labels from each other, we write the energy level number right before S, P, D, and F. The third quantum number is called the magnetic quantum number and is shown by ML. To find out what ML is, we need to dig even deeper into the energy levels. If we dig more, we will find orbitals in the sublevels. I'm showing the orbitals by ovals. This is just a conceptual representation. As you can see, the first energy level's sublevel has only one orbital. Let's go to the second energy level and see how many orbitals we can find. We already know that the second energy level has two sublevels. The first sublevel has one orbital, but the second sublevel has three orbitals, two more. You can now see how many orbitals the atom has in the third energy level. The first sublevel 1, the second sublevel 3, and the third sublevel 5. I'm pretty sure you learned what is the trend. You can pause this video and try to guess how many orbitals the atom has in the fourth energy level. I wait a little bit. Alright, I'm assuming that you already got the answer. You can see the orbitals in the fourth energy level. Everything is the same as what we had in the third energy level, except that the fourth sublevel has 7 orbitals. We give numbers to orbitals and they are called the magnetic quantum numbers. ML starts with -L and ends at positive L. Just reminding that L is the angular momentum quantum number. Let me provide you with some examples. The first energy level's sublevel has an angular momentum quantum number of 0. Since here we have only one orbital, ML equals 0. The first sublevel of the second energy level has the same situation. L for the second sublevel of the second energy level is 1. Here we have 3 orbitals. The magnetic quantum numbers associated with these orbitals are -1, 0, and +1. I hope this is clear enough. The rest of the orbitals can be numbered by the way I just talked about. The fourth and last quantum number is called the S-spin quantum number. It is shown by ms. Ms is either positive half or negative half. It demonstrates the direction of the electron spin. If the electron spins in this direction, ms is positive half, and if it spins in the opposite direction, ms is negative half. You can imagine orbitals as high probability clouds that can hold 2 electrons. The only condition is that the electrons must spin in the opposite directions. Now that the 4 quantum numbers are introduced, it is the time to talk about a very important principle called Pauli's exclusion principle. This principle simply states that no 2 electrons can have the same 4 quantum numbers. For example, the 4 quantum numbers associated with this electron are these. If I grab another electron, let's say this one, its 4 quantum numbers are these. As you can see, the 4 numbers are never the same. Again, we can see the atom structure, the energy level, sublevels, orbitals, and electrons. This table summarizes some of the concepts I talked about in this lecture. This table shows the energy level, the number of sublevels, orbitals, and electrons in each energy level. Using this table, we can come up with three equations. One to calculate the number of sublevels in each energy level, one to calculate the number of orbitals in each energy level, and one to calculate the number of electrons in each energy level. If you have these equations in memory, there is no need to refer to this table anymore. In this lecture, I covered the energy level concept and introduced the four quantum numbers, plus Pauli's exclusion principle. In the next lecture, I will cover the energy diagram. Thanks for joining another lecture of Peacademia.